All right, let's keep on keeping on. So the next topic here as it relates to UV-Vis molecular absorption spectroscopy is the actual equipment or apparatus that you would use to perform these measurements. The first thing you need to know is that this device is called a spectrophotometer. It's the name of the device that people use for UV-Vis molecular absorption spectroscopy. It's a pretty simple device, and they're always designed to measure transmittance. And of course, through mathematics, you can convert that to an absorbance as we learned earlier. But they're really designed to measure transmittance. Now, there are many different types of spectrophotometers. We're going to consider some of them, but they all have generally the same parts, okay? The first part that we're going to need is the spectroscopic source. This provides the light to probe the sample. The source can be pulsed, it can be continuous in time. Most of the time, there are continuum sources, which means it gives us a broad band of wavelengths. Sometimes they can be monochromatic, like lasers, for instance. They're only one color typically. Then what you do is you take that light from the source and you pass it through a wavelength selector. Very often, this is called a monochromator. But we need some way to select only a very narrow band of wavelengths for our analysis. Very important part of the device because remember, Beer's law is only valid for monochromatic radiation, okay? So you need to have monochromatic light, you need to have a wavelength selector. Now, after we pass the light through the wavelength selector, we've got one very specific color. We pass the light through our sample. It's usually held in a device called a cuvette. Then the light which comes out the other side is incident upon a transducer or a detector. A transducer or a detector will take a physical phenomenon like light intensity and convert it into an electrical signal that can be read out on a meter and logged. And that's our last component, is the readout. Where do we get our information from? Okay, so all spectrophotometers are going to have those parts. Let's break them down in a little bit more detail. Okay, now I'm not going to have time to go into extreme detail on every single part. Again, if you really like this topic, you might want to take instrumental analysis with Dr. Pappas, and he'll be able to tell you a lot more because that class doesn't cover the whole first half of this one, okay? But spectroscopic sources provide light for our experiment. Now, they can be either line sources or continuum sources. What's the difference between the two? Well, a line source basically already is monochromatic. It's basically one wavelength, like a laser, for instance. Lasers generally provide one and only one color or wavelength of light. They're monochromatic, they're line sources. Atomic vapor lamps are also line sources. Now, a continuum source give us many wavelengths at the same time. Lots of different wavelengths. You might say it's a white light source. It produces many different colors, many different wavelengths or frequencies of radiation. Our sources for spectroscopy can really be either. Now, usually the devices that we're going to talk about are going to employ continuum sources. That's pretty typical, okay? But it doesn't have to be. It can be a line source. Now, the source can either be continuous or pulsed in time. I'm going to make a plot of intensity of output power versus time. A continuous source would basically have more or less continual output power. On the other hand, a pulsed source might be off and then on, and then off and then on, off and on. You get the idea, right? This is a pulsed source. Now you say, well, why in the world would you use a pulsed source? Well, sometimes there's advantages to that because when the light beam is off, it's dark, basically, so that gives you 0% T reference. And then if this higher light level corresponds to your sample and you know what the 100% is, there's some advantages of having the pulse source because in one complete cycle, you may be able to get a transmittance reading. Okay, more on that later. Regardless of what type of source we use or what exact source, there's some desirable characteristics. These are things that are characteristics of our source that we would really like our source to exhibit. And the biggest one for UV-Vis molecular absorption spectroscopy is output power stability. Exclamation points, right? You need your lamp or your spectroscopic source to have a very, very, very stable output power. You don't want it to get dimmer and brighter over time. Because if it does, how are you going to detect an absorption on that very noisy baseline? It's almost impossible. So our lamps have to be very stable output power. We'd like it to be bright or powerful enough to detect easily. We don't want to go into a lot of trouble to have to detect the light. Of course, we need it to emit radiation at the wavelength that we're interested in measuring. If our source doesn't produce the correct color wavelength, boy, we are in trouble. We also like it to be low cost, durable, and easy to use. Also important, there are certain spectroscopic sources which meet all of these characteristics, or most of the characteristics, but there's not really a perfect source, okay? They are listed over here in this table. One type of spectroscopic source, it's used a lot in fluorimeters. We'll talk about that in a separate video, are xenon arc lamps. The high pressure gas envelope filled with xenon gas, as the name suggests, and you create a little electrical arc in there, and it glows. It gives off a very, very pretty white light, as it turns out. It's a continuum source producing wavelengths from 250 to 600 nanometers. It's a very nice, bright point source of radiation. Xenon arc lamps are actually used in IMAX projectors as well. Very, very beautiful, bright color light. There are also hydrogen lamps, and D2 is an isotope of hydrogen called deuterium. It's an abbreviation for that isotope. It's got an extra neutron. Now, the deuterium lamps or the hydrogen lamps are UV sources. They produce light from about 160 to 380 nanometers. We're actually going to use the deuterium lamp a lot. I want to talk about that in a second because it's used a lot in spectrophotometers for the UV region. The next lamp is tungsten halogen or tungsten halogen lamps. We kind of group these together. Generally producing light from about, this one's a little bit lower, about 250 to 2500 nanometers. This one's 350 to 2200. Basically, both of these have a tungsten wire inside of an evacuated glass envelope. You pass a current through the wire. The wire heats up and it gets hot and it basically glows, almost like a hot chunk of iron. Now, if you get it hot enough, you can get it to produce visible light, particularly the tungsten lamp, and even near IR, right? The wavelength extends out to about 2 microns. But the thing is that the tungsten lamps have the drawback is if you get it too hot, the lamp will just burn out, the filament will just burn out. And I'm sure many of you have experienced that. The tungsten halogen lamp is a variant of the tungsten lamp in which when they manufacture it, they purposely put a little bit of a halogen inside the glass envelope, and most commonly, or commonly they use iodine. And interestingly enough, the tungsten will react with the iodine to make a gas phase molecule. And that basically diffuses back to the hot filament where it decomposes. So if you've got this filament, let's say that's made out of tungsten, right? You pass a current through it, it gets really hot. Well, the tungsten atoms basically come off to the gas phase. And in the gas phase, they can react with the iodine or the halogen, which has been added. And that basically causes them to form a stable form rather than deposit onto the surface of the glass where they're just basically removed due to condensation on the glass. But instead, they form this other gas that diffuses back to the surface where it actually decomposes and the tungsten redeposits on the surface. It's kind of like a recycling approach. Well, anyway, if you do that, you can get a little bit hotter lamp. And because of that, you can get a little bit further down into the UV, but still not a great UV source. Then we've got our 3 infrared sources. If you're doing infrared spectroscopy, you might be using a Nernst glower, nichrome wire, or a glow bar. The nichrome wire is kind of like that stuff that's in your toaster. You pushed a button in your toaster to make some toast in the morning or whenever you eat toast. And those little wires heat up, right? Because infrared radiation, we kind of perceive that as heat energy oftentimes. The wire has a little bit of light given off, maybe in the red or orange portion of the spectrum, but most of its radiant energy is in the near IR or the infrared itself, where we cannot see. The emission can expand all the way out to 20,000 nanometers or 20 microns. We can't see that, but of course your toast experiences it, it absorbs it, and then kind of browns nicely. Hopefully it doesn't burn, right? So these are different spectroscopic sources. Now let's review a few that are specifically used for ultraviolet visible molecular absorption spectroscopy. The first one I want to tell you about is the deuterium lamp D2 lamp. Now remember, deuterium is an isotope of hydrogen. It's got one extra neutron, okay? We're going to take this deuterium gas and put a low pressure of it inside of a tube, basically, that's sealed off from the outside world. Typically, that tube itself, or maybe if you zoom in right here, you can see these little windows. Light's going to pass out of that little window, okay? That little window is actually going to be made out of this quartz-based material. And the reason why is because it's optically transparent, or it's transparent to ultraviolet radiation. Okay? We need that window to be transparent to UV radiation because the deuterium lamp is going to be our prime source of ultraviolet light. This is a UV source, as it turns out, okay? Your book will tell you a little bit more about the operation of it, but what I want to focus on is the spectrum, which is down here at the bottom. This is 200 nanometers, this is 400 nanometers. This is all in the UV, not even in the visible at all. And I also want to point out that this, before we go any further, is a log scale, not a linear scale. Now, there's a lot of units and terms here. Basically, what this axis tells us, make things simple, is the intensity or the brightness of light emitted by one of these deuterium lamps from 200 to 400 nanometers, the emission spectrum. And what we can see is it looks like the light intensity peaks out right about here, which is somewhere around 250 nanometers. It drops off a little bit below that and then drops off more at higher wavelengths. Now, since our y-axis is a logarithmic scale, we have to basically pay attention to this, think about it a little bit. Right here, we've got 10 to the minus 1 power, and then here it's 10 to the minus 2. So between this point and this point, there's actually a 10-fold difference. And down here, it's 10 to the minus 3. So this scale from the very top to the very bottom is about a 100-fold difference in brightness. Okay, so think about that for a second. If we go from up in this region down to here, that's a 10-fold drop in the output intensity from about 250 to about 350 nanometers. Okay, now we're still getting some light, 350 to 400 nanometers, but boy, the intensity is really dropping very fast, isn't it? It's not so bright out here once we start getting near the visible portion of the spectrum. But it is quite bright here, from maybe 200 to 350 or so. So the deuterium lamp is an excellent source of ultraviolet radiation, but not so bright once we get out near the blue or the visible. Okay. So because of that, we're going to use the deuterium lamp almost exclusively for our UV or ultraviolet source in spectrophotometers for molecular absorption spectroscopy. Almost universally, these are used, okay? There's a couple of electrodes inside the envelope. Basically, you put the deuterium in there, you turn on a relatively high voltage, and this causes dissociation of the deuterium and emission of a UV photon. And because when the deuterium dissociates or breaks apart, each of the atoms involved have a different amount of kinetic energy imparted to them. The exact wavelength which is emitted depends upon how much kinetic energy the atoms get, and this causes basically a nice broadband or continuum emission in the deuterium source. So that's our UV light source. Now, for visible, almost universally, we use tungsten lamps, right? Because these are cheap. These have been around for a couple hundred years now. Well, I guess 100 and some. And what this is, if you think about the light bulb in your closet that you screw in, right? Traditional light bulb, it's got a little wire inside that's made out of tungsten. And you pass an electrical current through that wire, And lo and behold, the electrical current causes heating in the wire heats up and it glows. It gives off radiant energy that we perceive as light. Now, because these have been around for so long, they're well understood, their mechanism of operation, and they're widely manufactured. So very, very, very inexpensive as a result, okay? So it's an inexpensive source, and it can be made reasonably stable if the current through the device is controlled. Now, the interesting thing about this is it makes a really good visible light source, but no UV, okay? And to see what I mean by that, let's zoom in to the spectrum, which is our plot of intensity versus wavelength in nanometers. Now remember, 400 to 700 is our visible range, right in through here, okay? Notice that if we look at the output intensity distribution or spectrum of our tungsten lamp, we get some visible light, but most emission actually occurs in the NIR, or the near infrared region, which is out here past 700 out to 2 microns. Okay, so while the tungsten lamp can certainly serve as a spectroscopic source in the visible, and it does produce some visible light, and actually we use these tungsten lamps, again, almost universally for the visible light source in our molecular absorption spectrophotometer. Most of the light emitted is actually in the near infrared. So, in recent years, there's been a lot of talk and action towards replacing tungsten lamps in your homes for lighting applications, right? You might want to switch to fluorescent-based light or an LED-based light. And this is actually a big reason why most of the light that these lamps give off are in the near infrared. We can't see that. Now, if we put our hand up to the bulb and it feels warm, we're experiencing that, we're feeling that infrared light, but we can't use it for lighting our homes, right? So some of these other light sources are much more electrically efficient. So nonetheless, this little wire inside can get up to about 2,900 degrees Kelvin. It glows, gives off radiant energy, and we can use that for our spectroscopy, and it's commonly done. Now, what about our wavelength selector, which was our next key component? I'm just going to give you an overview of how this works rather than too much detail on the physics behind it. There's parts of your textbook and other textbooks where you can learn a lot more about the physics behind it. It's kind of interesting, actually. But nonetheless, this wavelength selector is called a monochromator, literally meaning one color. It's a device which makes one color, or one narrow wavelength band. There's a couple different types of monochromators for scanning-based spectrophotometers. These are ones that you can actually change the wavelength or scan the wavelength from low to high wavelength and change the wavelength. We generally want that capability, by the way. Okay, now there's two different monochromators that you can use. We can use one based on a diffraction grating, and we can use one based on the prism. The one that is most popular, in my experience, is based on the diffraction grating. And that's actually the one shown on top. But to start off, let's talk about the prism-based design. If you're going to use a monochromator, sometimes it comes in a big box. Okay, so that's why I circle it here. There would be the spectroscopic source over here. This would be our light bulb, or light bulbs producing radiation, which would be incident upon the first part of our monochromator, which is called the entrance slit. Entrance slit, SLIT. What in the world is the entrance slit? Well, it's a tiny little hole or opening that the light can basically make it through. Now you say, well, what's the purpose of that? Well, the purpose is to provide what's called a point source of radiation, which is important in optics. It basically creates a very specific point in space that we can use as the source of our light, or where our light is emanating from. You say, well, why do I need that? Well, because what I'm going to do is I'm going to take a collimating lens. This is a lens, and I'm going to place it at a focal length away from that entrance slit. And what that lens purpose is, as the name suggests, to collimate the light. Okay, so what does that mean, right? Well, it basically means to take the light rays and make them parallel to one another. Like, for instance, a laser beam that you can shoot across the room. It stays as a nice thin pencil of light, a beam of light. That light is highly, highly, highly collimated. All the rays traversing the room are parallel to one another. That's very different than a flashlight or a light from a tungsten lamp in your closet. In those spectroscopic sources or those sources, the light, it just spreads out in all directions or many different directions, right? But the laser beam is one beam, pencil of light. So this is what we mean by collimated, that the rays are all parallel. And we can achieve that by using this entrance slit collimating lens combination. That's actually important. We have to make our rays parallel, but before we send the rays to our dispersal device. Well, let's say dispersion device here. Now in the prism-based design, it's going to be a prism. The rays will be incident upon this prism. And the prism actually is going to spread out the different colors of the rainbow, so to speak, right? But the way that works is because the prism has a slightly different refractive index for all different wavelengths. Okay, in other words, the refractive index will change, it's wavelength dependent. And that's actually, which is oddly enough, also called dispersion, okay? So what happens then is that the different wavelengths will effectively spread out on a projection screen down here. They'll appear at different points because they're refractive differential. So we use the prism to achieve this differential refraction. And then we take a focusing lens to collect the light off of the prism, still the collimated rays. But after it passes through the focusing lens, we're going to focus the wavelengths down to specific spots. And because the prism differentially refracted our rays, the different wavelength spots will appear at different points in space on our focal plane. Okay, it's just a plane within this monochromator called the focal planes, where all the spots are focused down, basically the points. Now, at the focal plane, we're going to place the last component of our monochromator called the exit slit. The exit slit is another tiny little hole. Now, what's the purpose of that we place at our focal plane? Well, all the lights focus down, and remember the different wavelengths appear at different spots on that focal plane. Okay, so this would be one wavelength appearing here. Maybe that's red light, and then over here, maybe it's the blue light. Okay, and it'll be like the RGB pattern in between, right? Because every different wavelength is focused on a different spot, if I place this exit slit right here at that focal plane, only one wavelength band will make it through the hole in the exit slit, and all others will be blocked because that exit slit's not transparent. Only the color wavelength which makes it through will make it to the outside world, which I can then use for my spectroscopy. All the other colors will be blocked. You say, okay, well, I guess I get that. But how do I change the wavelength? You mentioned it can be a scanning-based instrument, right? I can change the wavelength from blue to red to orange. I can pick the wavelength that I want. And if you've ever wanted to use one of these in lab before, that's probably what you did in the experiment. So how does that work? Okay. Well, it turns out it's pretty easy. You just attach this prism to like a little cam that you can rotate, or a little knob that you can rotate, basically. And that actually moves this back and forth on our focal plane. It moves the spots back and forth, so you can easily tune what color of light you want. It's a very, very simple thing to do, and typically that's what happens. Now, the second type of monochromator is based upon a diffraction gradient. And this one, in my experience, is more popular, more commonly encountered. Has some similar parts. Okay, so down here we're going to have our light bulb. My light bulb producing light. Okay, we're going to pass the light through the entrance slit. Again, that makes a point source. I've got a collimating mirror here. Now, it's not a lens anymore. Now it's just a mirror, but it serves the same purpose. So place it at a focal length away from the entrance slit. It collects the light and reflects the light. But when it does, because it's this concave mirror, the beam is now collimated. just like the lens collimated the beam before, okay? All the rays are parallel, like the laser beam, thin pencil light moving across the room. So what happens next? Well, this is where the difference is. Down here, instead of using a prism, I'm going to use a device called a diffraction grating. In this case, it's a reflection grating, which just means that it's a grating, but the light reflects off of it, okay? And if you look really, really carefully at the surface of this grating down here at the bottom, you see like there's like this series like of well, it looks like this, right? A jagged edge in the drawing, right? And that's kind of on purpose that they drew that. And the reason why is because this reflection grating is not perfectly flat, but instead on the surface, a series of what are called grooves. Okay. Now, what is the significance of this? Well, if I was to draw it, it might look like something like this, okay? I have to bear with me, I'm a terrible artist, right? And so let me do this again, that's really bad. All right, so what I'm drawing here is a series of these grooves on the surface. It's like a zoomed in picture of what's going on down there on the surface. And there could be hundreds to thousands of these grooves every millimeter, combined with different groove densities. But they're absolutely crucial to the functioning of this device, as it turns out, because each groove acts like a point source of radiation, as it turns out, a point source of radiation. Now, back in physics, chemistry, something like that, one of these STEM classes, you all probably have experienced an experiment that looks like this. It's called a double slit experiment, where you take a beam of light and you find it incident upon two slits, hence the name double slit, two small holes, kind of like these exit and entrance slits, two very small holes, light is incident upon it. And one of the properties of light is that the wave-like property, or just wave-like properties in general, is that it diffracts or spreads out, right? Emanates from these openings or slits. So you tend to see like pictures or drawings like this as a result of this discussion. And in those drawings, they kind of make the point that at these points where the beams of light emanate from the slits and overlap in space, you can get what's called constructive interference. It basically means that the light emanating from the two different slits recombines at that point in space exactly with the waves exactly in phase. Because their intensity grows, you get constructive interference, essentially a bright spot, okay? And then there was the option or the possibility of destructive interference as well. Maybe you remember this. This is when the beams emanate from these slits, recombine in the far field away from the slits. And when they recombine, the wave fronts combine out of phase, thereby canceling each other out. And if you get destructive interference in one of these experiments, it's essentially like getting a dark spot. There's no light to be seen. So constructive interference, it would get brighter and a very bright spot, and destructive interference would be a dark spot. And it turns out that if you make a projection screen along a plane, what ends up happening is that you get a bright spot at certain locations And then in between, you get the dark spots. These will be like bright, dark, bright, dark, bright, dark. And this would be called a diffraction pattern. And again, I'm discussing a very specific wavelength. One wavelength, monochromatic light entering these slits, okay? So you get this pattern. Now, the thing is that because different wavelengths of light or different photons of light have different wavelengths, the exact location in space that these patterns appear, whether it be the light spot or the dark spot, will change with wavelength. They're wavelength dependent, the exact location that the interference pattern appears for a particular wavelength. So because of that, basically what happens in one of these devices is that at this reflection grating, each individual facet or groove, remember there's grooves on the surface, each groove acts like its own independent mirror or a point source of radiation. Just like we had those two slits in that experiment I was just telling you about, well, each groove on the surface of the grating can act like its own point source of light. So when the collimated input beam comes in and strikes that grating, every single groove, and again, there's thousands on that grating, can act like its own point source and diffract the light off of it in this direction. Think about that for a second. What's going to happen? Well, from each individual surface, those wavefronts could what? Spread out. And in the far field, they're going to recombine either in phase and out of phase, depending on the exact spatial extent. So where does that occur? It turns out it's going to occur down here in the focal plane. So the light which diffracts off the grating is collected by a concave mirror and then focused down. Sometimes this is called a focusing mirror. Okay, let's focus down again at this plane, this focal plane, where I'm going to place an exit slit as well. But the light which is diffracted off the grating, remember it was spreading out and it's got to appear its constructive interference at a particular point. Well, each wavelength, after focusing, will produce bright spots down here on this focal plane. So maybe the blue light appears right there. Okay. Maybe over here is some, oops, let's see, let me switch back to my pen. Over here, there's some green light. They recombine there. And then maybe here there's yellow. And then here there's red. And then maybe on into the IR and the UV down here, right? There's a light we can't see. But the point is, if I introduced polychromatic radiation, light of many different wavelengths into this device, because each wavelength diffracts off the grating differently and recombines at slightly different points in space, I can spread that out across the focal plane at the exit slit of my monochromator. And because this focal plane has a small hole at a very specific point, only one color of light will make it through at a time. Here, maybe it's the blue light that makes it through. Very specific wavelength, okay? I've chosen to talk about colors here just to be instructional, but you know, I can convert that to a wavelength as well, and only a specific band, a narrow band of wavelengths would make it through the hole. So you say, okay, I can see how maybe that would block all the different colors because the exit slit would basically shadow it, right? But if I want red light, how do I get it? Okay, well, easy. You take a rotating cam, attach it to some sort of knob on the front panel or mechanical drive. You basically just rotate this gratings angle with respect to the incident collimated beam. What that actually does is it moves these spots back and forth on the focal plane. So you can get whatever color passband you want. So this is the monochromator based upon a diffraction grating. So this word right here. There's also one based on prism. They're similar, but they have different wavelength dispersal devices. And I certainly invite you all to check out chapters 18 and 19 in your book if you want to learn more about this. Okay, there's actually a bit more physics, or at least you could talk about this from a physics perspective and interference of waves. It's actually pretty interesting to look at that. I just think for our purposes in class, we don't necessarily need to go through that when we're just giving you an overview. So some more about instrumentation. Where we're going to put our sample. Well, the sample cell for UV-Vis molecular absorption measurement is called a cuvette. Cuvettes, okay? Cuvette is nothing more than a sample holder. It's a glorified sample holder. I suppose that beyond just being a sample holder, we engineered these cuvettes to take on a very specific form or dimension. Some pictures of these cuvettes are shown over here. The most common one would be this one for typical UV-Vis molecular absorption measurements. They're typically about 3 centimeters high, and the depth is almost always 1 centimeter. And earlier, remember I said that the path length is typically 1 centimeter in molecular absorption spectroscopy. This is actually why it's typical to use a 1 centimeter cuvette, and the light basically traverses that direction through the cuvette. Notice they are typically square. Sometimes you'll see cuvettes in inexpensive devices as being like test tubes or cylinders. Cylinders, yep. My pen is, I think the battery's gone dead. They're cylinders, and you pass the light basically through the bore of the test tube. Now there's a problem with that. Let me explain. If you look at the cylinder top down from the top, you pass the light through the cylinder. Does every beam have exactly the same path length? I would say no. The beam that goes right through the middle will have the longest path length, and say this beam on the right will have a considerably shorter path length. So usually we don't like to use cylindrical cuvettes. We like to make them square. So that everywhere through the sample, we get exactly the same 1 centimeter path length. Okay, so it turns out this holds about 3 milliliters of sample typically. It's a very standard cuvette. The major design criteria that you need for cuvettes, they need to be optically transparent in the spectral region of interest. So for visible light, 400 to 700 nanometer, if you can see through it, like you can see through a window, that means it's optically transparent and you're good to go. However, for UV light, situation is not so easy because we can't see UV light. So it's at least possible that you choose to pick a cuvette that is not UV transparent. And for the longest time, you probably have seen, or maybe you have seen, cuvettes that are square like this, made out of various different polymers or plastics, okay? And they're very popular because they can be used as like single-use cuvettes. You basically run your sample and then kind of like throw it away, dispose it. You don't have to worry about contamination, which is always, I guess, kind of convenient, right? If nothing else. But if you're going to use these disposable plastic cuvettes, you want to do a little bit of research before you just decide to adopt them. You want to know what it's made out of and what its optical transparency window is. And the reason why is because historically, some of these cuvettes are not UV transparent. Okay, some of them have not been UV transparent. And regular glass is also generally not considered UV transparent. So if you consider this figure right here, what it is a list of transparency windows for different materials. This is the ones to look at. I don't think they have a plastic entry here, but the ones to look at, I'm going to try to highlight these 3. These are typical materials that you might make cuvettes out of for molecular absorption spectroscopy. You can make them out of silicate glass, Corex glass, slightly different compositions, okay? And then lastly, fused silica or quartz. Silicate glass, the type of glass that you might have kind of around your house. Its transparency window actually ends slightly less than 400 nanometers. Now, it can extend all the way out to about 2 microns. But silicate glass is not UV transparent down well below 400. So if you try to use just a normal silicate glass cuvette for UV absorption measurements, you might be kind of frustrated and disappointed. because you might find that there's not really any light getting through the cuvette, and you want to usually make absorption measurements on your sample, not your cuvette. So you can't use something that's not transparent in the spectral window of interest. Same thing with the plastic. Oftentimes they have a UV cutoff below 400, but it doesn't necessarily get you down to 250, 240 nanometers. So you might have to actually look at the manufacturer's specifications. These days, they've recognized that people like to have plastic cuvettes which are transparent in the UV. So they've done a bit of engineering to try to make them more UV transparent, push the limit down into the UV. So if you look at the manufacturer specification for the cuvette that you're actually using, you might find that it's suitable, okay? But you always have to kind of pay attention to it. I guess that's my point, okay? Now, traditionally, if you wanted to make measurements in the ultraviolet, you would have to get quartz cuvettes. This would look more or less the same, but the walls and windows would have to be made out of quartz, which is UV transparent well down to below 200 nanometers. Now, doing so would allow you to probe the UV. However, these quartz cuvettes can be pretty expensive. Historically, you might buy them in what's called matching pairs for reasons that we'll understand as we progress in the lecture in this chapter. And a matching pair, which would be a set of two that are almost identical, might cost you $500 or $600. They're not cheap, okay? They're also very fragile. They tend to fall apart, so not necessarily very user-friendly. But that's what you'd have to do to get down into the UV. So the moral of my story here is that if you need to make ultraviolet molecular absorption measurements, which actually is commonly done, they're down to 200 nanometers, very commonly done, you need to be cognizant of what your cuvette is made of and be sure that your cuvette is UV transparent. It's very, very important. Now, there are many other materials here on this. The ones down here are all salts. We typically use these for infrared spectroscopy because they're all binary salts. Same as perhaps lithium fluoride, although lithium fluoride can also be used down here in the deep UV region of the spectrum, but they're not commonly used for cuvette materials for molecular absorption spectroscopy. A little bit more about these cuvettes. It turns out that while this is kind of like the standard design, there are many other designs that you can purchase if you're really interested in other options for cuvettes. I'll kind of like zoom in a little bit so you can see this. This is always kind of fun to look through catalogs for different manufacturers. There's what they call these micro cuvettes. It became apparent that even though this cuvette only holds 3 milliliters, which doesn't sound like a lot, certain times, maybe like biochemical type examples, the quantity of material that you have to make a measurement on can be very, very, very small. And the material tends to be very, very precious. Maybe it's very expensive. You can only afford a small amount of it. The quantities involved are very small. In that case, 3 milliliters is just too much volume. Maybe you need 100 microliter sample volume, that type of realm, right? If that's the case, you can use these micro cuvettes. The way that this is another example of that, okay, as well. The way that this basically works, or the advantage of it, is they manufacture builds the cuvette in a different way to minimize the volume of sample used while still keeping a 1 centimeter path length. And the way they basically do that is the walls here, this is like a centimeter wide on a normal cuvette. Okay, but what they do is they push the walls on the side together. So the front of this cuvette is still the window, and the back is the exit window. So we're going to pass the light up through this axis, basically. And in doing that, you can see that since they only pushed in the side walls, the path length through the sample might still be 1 centimeter. But because they pushed in the sidewalls considerably, the volume that's required to fill up this cuvette has now been reduced a lot, hasn't it? So we can reduce the sample volume, but maintain the 1 centimeter path length. It's important to maintain that path length because that really helps our sensitivity. Remember, the absorption that we see is directly proportional to B, the path length in the Beer-Lambert law. So we don't want to sacrifice the path length. We want to keep that as big as possible, and these cuvettes allow us to do that. There's also what they call sampling cuvettes. where you can actually flow through sample and pump it in and withdraw it to the outside world, flow through cuvette, and that way you can change the sample over time, all the while making absorption measurements. It's kind of interesting. All right, many different options. Now that we've got the light spectrally selected with our monochromator and passed through our cuvette in our sample, how are we going to detect it? Well, we need to use what's called a transducer or a detector. This is a C. Transducers take a physical phenomenon and convert it to an electrical signal which is proportional to the magnitude or intensity of the physical phenomenon measured. Now, there are many different types of light detectors that we can use. We're going to talk about just a few of them, but desirable characteristics include high sensitivity or high response. In other words, we would like to get a large electrical signal for a small amount of light. We want them to not be noisy, low noise, easy to use and durable, hopefully inexpensive as well. We would like them to respond over a large range of wavelengths, but we can measure many different wavelengths. We'd like them to have a fast response. We don't want to wait around for our answer, right? And lastly, very important, the measured electrical signal produced must be linearly proportional to radiant power. Now, there are several different types of detectors. There are phototubes, and we're actually going to start with that one. And we're going to talk about photomultiplier tubes, which is much more sensitive. Silicon photodiode, and then photoconductive cell photovoltaic cells. We're really going to consider these first three because they've become popular these days. Really the last one, the photodiode, is starting to take over. But we'll start at the beginning and talk about phototubes. This is a little bit more of a historical detector, but nonetheless, they're still commonly encountered. Phototubes will convert light intensity into a measurable electrical signal by using something called the photoelectric effect. Photoelectric effect. Now, what this is basically is if you have a surface of a metal or some substance, okay, and you shine a beam of light at it. If that beam of light is of sufficient frequency and energy, a really interesting thing happens right here at the surface. We can drive a photoionization event. In other words, a metal atom on that surface may absorb the light energy, producing M+ ion and an electron. An M+ ion and an electron. Now, what we can do to make a detector is just simply collect these electrons which are produced. And if we pass electrons through a wire, we produce a current, which we then are pretty good at measuring, right? So one photon, one electron, we just collect the electrons and produce a current. Now, the trick to making this work is that our energy of our photon needs to be sufficient to ionize the metal of interest. If the energy is insufficient, no ionization will occur. No electrons will be produced. Okay. So to make a detector, all we need to do is build an apparatus that looks like this. This is our phototube. Our beam of photons is incident upon this tube. It's a glass tube, basically, and inside there's a couple of electrodes, the cathode and the anode. The anode is simply a wire. This is where we're going to collect electrons eventually. But the photon comes in and it strikes the photocathode. At the photocathode, that's where the electrons will be produced through one of these ionization events, photoionization. The electron which is produced is going to be accelerated towards the wire anode where it will be collected and pass through a wire to the outside world. Now, these electrons, they're not going to be collected at the anode easily or freely, we'll say. We've got to do a little bit of work to collect them. How do we do it? Well, to use this device, we need an external power supply. Here it's biased at 90 volts DC, which means a constant 90 volts. Notice that the anode, if we trace it back, here's the positive electrode, and that's by design, because we know that electrons are negatively charged. So if I produce a negatively charged electron, it's going to be attracted to the anode if I bias it at 90 volts. The other electrode, the cathode, is actually the negative electrode. If you look at it, right, this is the negative sun. If I follow that back up, see it's connected to the cathode. Can't see the wire running through the base, but it's there. Right? So that cathode is negatively biased, 90 volts relative to the anode in this particular example. So if electrons are produced by photoionization events from my photon beam striking the photocathode, the electrons will quickly be accelerated to my anode, or they'll produce an electron flow or a current in the external circuit. I simply need to measure that current, and that current will be directly proportional to the light intensity. Now, the trick in making this work well over a broad range of wavelengths is making my cathode out of a material that's easily ionizable. Because if that's too difficult to ionize, it's not going to work for visible or ultraviolet photons. I need to make the material on that cathode pretty easy to ionize so that even visible photons can ionize it. So that cathode is frequently coated with a material that's easy to ionize. And this is oftentimes an alkali metal or metal oxide. Things on the periodic table, briefly we'll say, looks like this, right? That's not, I got a little bit too excited on the left-hand side, but nonetheless, the elements down here in this corner at the bottom left, those are the ones which are easy to ionize. They have lowest ionization energy, okay? So we typically make material on our cathode out of those elements. And you'll see that quite frequently because they're just the easiest to ionize. You've got to drive the ionization event if you're going to make a photocurrent. But nonetheless, it's kind of a cool application of a physical phenomenon to make a useful detector. Now, the next type of detector I'm going to tell you about is the PMT, or the photomultiplier tube. This is another engineering marvel, as it turns out. Now, this one is still based upon the photoelectric effect, just like the phototube was, okay? It's the exact same idea at first, but then things change. Now, to see how things change, I'm going to zoom in on this figure right here, okay? All right, a lot going on here, so let's stay on top of things. Now, the photon is going to come in from this direction. HV is the energy of a photon. Photon comes into the tube. What happens? Well, the first thing it does is it encounters this electrode right here, which is our photoemissive cathode. That's that electrode which is the most negative voltage applied to it, the most negative potential. It's a photoemissive cathode. So again, it's made from a material that's easily ionizable, and we can make M plus and E minus, with E minus being our electron. So we coat that cathode with a material that's easy to ionize. If light comes in and it strikes that cathode, electrons will be produced, just like the phototube. Now, in the phototube, we collected those electrons, making a current. Nothing wrong with that, but maybe we could do something a little bit more innovative. What's that? Well, let's say an electron is produced. Now, in the phototube, I simply collect it, but I'm not going to do that here. Instead, I'm going to accelerate that electrode towards another electrode, which is called a dynode. And this is the difference between a photomultiplier tube and the regular old phototube. This dynode is also coated with easily ionizable material. also coated with an easily ionizable material, such that when the electron comes in and strikes the dynode, which I'm going to call D1 because it's the first dynode, there'll be more, okay? But the electron comes in, strikes the first dynode, amazing thing happens. If I'm writing it in terms of a reaction, like a chemical reaction, it's usually not written that way. I'm just writing it to explain, okay? But an amazing thing happens. The electron is accelerated towards the dynode, it's sped up, right? And it collides with the dynode in an energetic way. So that when the electron collides, multiple electrons are produced, maybe somewhere on the order of 5 to 8 electrons for every single electron. Okay, so one electron comes in, but maybe 6 or 7, and these are my 6 electrons in my cartoon picture, are released from the dynode surface. And they're accelerated towards D2, the next dynode. And guess what? This is the second dynode. It's still coated with this easily ionizable material. So when those 5 or 6 electrons impact dynode 2, each one, we're going to get this multiplication or amplification. Now, instead of having 6, maybe we've got 36 moving its way to dynode 3. And we just do this again and again and again. And we get like exponential growth in the number of electrons present inside this evacuated cylinder, this photomultiplier tube. Now, eventually, we kind of make our way around the circle, and we sort of run out of space inside the tube. But it turns out all these electrodes are really close together. It's pretty impressive when you look at one. In this particular design, there are 9 dynodes. So we do this amplification, sort of around in the circle, and we get to the 9th dynode. And then after that, we kind of run out of space, so we're done. So what do? We put one more wire electrode, the anode, inside, and any electron which comes off the dynode gets accelerated to the anode. That last dynode, dynode 9, gets accelerated to the anode, where it gets collected, fed to the outside world, producing a current that we can easily measure in an external circuit. Now, if you were to see a photomultiplier tube, it would look a lot like this. And this view that we just talked about would be a view from the top down, basically. So like from this direction, if you were to see it. It's hard to see because there's lots of electrodes in a very small place, okay? And even if I blew up this picture, we wouldn't be able to see all the electrodes, unfortunately. But that's what's going on inside one of these photomultiplier tubes. So it's oftentimes said that these photomultiplier tubes have a gain or an internal amplification. For every one photon that goes in, if that produces a photoelectron, maybe we get somewhere on the order of 1 million electrons collected at the anode for every one photoelectron. There's a huge gain or amplification factor. So because of that, these detectors are extremely sensitive, can detect very low levels of light, even single photons of light energy. Now, to use one of these, you have to bias the device or turn on a voltage with an external power supply. And usually, it was always a DC voltage, right? But usually, you need a reasonably high voltage. You can read that it's 900 volts DC. You might even go anywhere from 800 to 1200 volts, would be kind of typical for a 9 dynode device. And that 900 volts DC, you have to have an external power supply to power this up. And it's certainly necessary to make this device work. And the reason why is because to make it work, what you have to do, the electrons don't fly to the next dynode automatically, right? You have to accelerate them there. Now, they're charged, so you can accelerate charged particles by placing them in an electric field. So the first electron which is produced, if you want it to go to that dynode, you got to make it more positive voltage than the cathode. So this is our most negative point, right? And then if you want the electrons to go to dynode 2, well, gosh, you better make it more positive, right? And I'm using the number of positive signs here as an indicator of how positive each successive dynode is. But you get the idea. You got to make each successive dynode more and more and more positive. And the way that that's achieved electrically is using this circuit down here on the bottom, which is called a voltage divider. As it turns out, you use a power supply of 900 volts across a series of resistive elements. These are resistors which are usually built into the base of this tube right here. And D1, 2, these are the individual diodes, okay? So the last diode is basically the most positive point in the chain, and the first one, or the cathode, is really the most negative point in the chain. And each subsequent diode basically is more positive than the preceding one by a factor usually of like 1/10 in this case of the original voltage. Because each of these resistors, these little squigglies, are all meant to be resistors, and we make them basically all the same. So the voltage drops evenly between points over 10 different points. Okay, so that's the circuit that you would use to achieve this, is so-called voltage divider, but very, very sensitive devices. Now, silicon photodiodes, another type of light detectors. These are solid state light detectors, which are much more recent or modern. Very interesting how they function. Basically, what we're going to do is we're going to make some semiconductor material. Now, usually when you hear about semiconductors, right, you think of like Silicon Valley, right? Well, and the name even here is silicon photodiodes. So what you're basically going to start with to make a semiconductor is some silicon. And silicon's an interesting material. People have gotten good at making it very, very pure into thin wafers. Very, very, very pure. If you want to make a very pure silicon, you can achieve that. And silicon is in the same group as carbon. It's got 4 valence electrons natively. And if you make a pure crystal of silicon, I wish I had a white pen, but if you made a very, very pure crystal of silicon, let me zoom in. I'll explain what I want to communicate if I zoom in, because this figure doesn't show it. Pretend this one is not here, okay? And I want you to pretend that this is silicon for a second. If you made a very pure crystal of silicon, it would look something like this. The circles are the silicon nuclei, and these little dots represent the valence electrons. Now, each silicon atom will be surrounded by 4 others, forming a perfect crystalline lattice. And since each atom has 4 valence electrons associated with it, if each atom shares with 4 others, you basically make this perfect crystalline arrangement, or every atom is octet satisfied, if you want to think about it that way, okay? And let silicon be made very, very pure, so this can actually sort of be achieved to a large degree. Now, there's nothing wrong with doing that, and I guess chemically it's really quite interesting and sort of beautiful, right? It's this perfect crystalline substance, but from an electronic standpoint, it's not that great. And the reason why is because all these silicon atoms have these valence spots filled in. Each one has this perfect 8 or octet. So because of that, the silicon itself wouldn't be that great of a conductive material. So we're going to play around. We're going to change things up a little bit. Instead of just having a perfect silicon crystal, what I'm going to do is I'm going to dope my silicon, or I'm going to carry out the process of doping. And basically what that means is you're going to purposely add an impurity to kind of screw things up, okay? Now, if I want to add, there's a couple different things I can add possibly, okay? One thing I can add is an element from a group of the periodic table, which is one group to the right of silicon. Now think about what that means. Think about the periodic table. One group to the right of silicon. Those elements all have 5 valence electrons in their outer shell. Silicon's got 4, but if I go a group to the right, they've all got 5, don't they? So if I dope with an element to one group to the right of silicon, things change a little bit. Now that atom has to find a home in this crystal, which otherwise would be perfect. And that's actually what the original figure here is showing. Okay, we've doped in a little bit of this element with the extra valence electron. And that's kind of awkward, right? because now what was a perfect crystal has kind of been messed up with this doping process. And because I chose to add an element one group to the right, now my crystal has an excess of electrons. It's got too many. There's some there that just don't fit, right? So this type of material we call N-type material, and it's been N-doped. And for, I say negative, meaning it has extra electrons or an abundance of electrons. And they're there just because we purposely added an element that's got more valence electrons. This is N-doping. Now I can also make a different type of material if I want to. I can make a P-type material. What happens if I take my perfect silicon crystal and I add in an element, one group left of silicon on the periodic table? So silicon's got the 4 valence electrons, but if I go one group to the left, now those elements, they only have 3 valence electrons. So if I put those atoms into that crystal, well, they need to find a place to reside. And when they do, look what happens. There's a vacancy. In semiconductor physics, that's called a hole. A vacancy or an absence of an electron. It's a hole. Now, we're going to call this material P-type material. P, I guess you could say it's positive, okay? In reality, there's no positive charge carrier there. There's just an excess of holes. There's an absence of negative material, and charge carriers, an absence of electrons, okay? So there's these holes which are present in P-type material. So you can make N-type silicon, you can make P-type silicon, excess of electrons or holes respectively. Now, interestingly enough, if you do this doping process, you add electrons or holes, all of a sudden, the material which results is much, much, much more conductive than it was with just the pure silicon. And the reason why is because you've either added these charge carriers, electrons, which can move throughout the crystal and that is conductive, or you've added these holes, which can be filled in with electrons and allow conduction through the material. Okay, so the conductivity goes way up, right? Which is one reason why people sometimes dope these materials. So once these dope materials were produced, engineers started to kind of play around with these, back in the 50s and the 60s, and try all kinds of cool experiments. And modern electronics really rooted in all of that, as it turns out. But one thing they found is if they took an N-type material and a P-type material and touched them together to make kind of like a sandwich, you could create what's called a P-N junction. And I always like to joke around that chemists and physicists and engineers, we are all like the world's most creative people sometimes with the names that we call things, right? P-N junction. I mean, would you call it anything else if you put a P material next to an N material? I guess you could be creative, but they weren't. And these become known as P-N junctions. So it's easy to visualize what's going on here. It's just basically the P material up against the N-type material. Now, the P material, remember, has excess holes, and the N material has excess electrons. So right here at this region between the two types of materials, you can have an interesting thing occur. What happens is right there at the P-N junction is that a depletion layer can form. And it turns out we can either make that bigger or smaller. More about that, but just naturally, this depletion layer will form. Right here at the interface, okay, some of those electrons which are present in my N-type material may migrate just a little bit. We're talking about like micrometer dimensions here, okay, into the P-type material and start filling in holes. Now, if those electrons migrate to the P material to fill in holes, think about what's going on then right at that interface. the excess electrons have been removed and the holes which were present have been filled in. So if we make one of these junctions, if this process occurs, right there at that interface, it's going to pretty quickly become non-conductive. Reason being, well, the charge carriers have kind of annihilated one another at this, in this micrometer thick depletion layer forms. That's important in semiconductor because it's this little micron thick layer, this depletion layer. It makes this whole device non-conductive from, say, point A to point B, left to right. No current can flow through it, just natively. Now, what can we do about this, if anything? Okay. Well, we can bias the device, which basically just means to apply a voltage with a power supply. And we can forward bias the device, or we can reverse bias the device. And the only difference is the way you switch, the way you hook up the leads of your power supply. Okay. Let's just say that you bias the device in this way, forward bias. And this is a positive sign, this is a minus sign, okay? Now this is our N-type region, this is our P-type region. So in this crystalline lattice, we have an excess of electrons, right? Now, I think we talked about in the electrochemistry chapter that electrons are attracted to a more positive potential. So if the left side's more positive, the electrons are going to be drawn that way, to the left. Now, if I apply a high enough bias voltage, and oftentimes in silicon, that's usually about 0.7 volts, as it turns out. If I apply a high enough bias voltage, it's like a driving force that's pulling the electrons to the left. And if I do that, and I overcome a certain voltage point, I collapse this depletion layer. I basically destroy it because the electrons are pulled past the depletion layer, if you want to think about it that way, into the P-type region. So forward biasing about 0.7 volts essentially destroys this depletion layer, causing current to flow. Okay. Now, on the other hand, I could reverse bias. And that's where I hook up the voltmeter power supply leads in the opposite direction. Now I'm going to make this side negative and this side positive, right? And as we know, electrons like to be drawn towards the positive supply. So guess what? Any electrons which are in my N-type region, they are moving to the right, aren't they? Now in reverse bias conditions, think about that for a second. What happens to the depletion layer? Well, it was this micrometer thick, a couple microns thick, right at the interface. But if I reverse bias, that depletion layer grows. Its thickness grows, doesn't it? Because the electrons which were present in my N-type region, well, they're pulled away from the depletion layer. We don't get collapse of the depletion layer. It's actually going to grow here under reverse bias conditions. So this junction will not be conductive. Not conductive. N-O-T-C-O-N-D for conductive, okay? Depletion layer grows. So we can bias these junctions. Now, that's all interesting, I guess, from an electrical point of view. And actually what I'm describing is actually how an electronic device called diodes work. You basically forward bias it, and it's like a diode's like a switch, basically. It turns on or off. And if you forward bias it, it turns on, it can conduct current, as it turns out. But here, what we want to make is what's called a photodiode. Is that different? Indeed it is, because it's a light detector. Now, how does that work? Okay, well, I mentioned that there's this depletion layer at the interface between the P and the N region, the PN junction. And it gets worse in the reverse bias case, doesn't it? Interesting aspect of these materials is that it turns out that if a photon of light energy comes in and it strikes the PN region, if that photon is energetic enough, it can actually create an electron hole pair right at that interface. And if this electron hole pair is created, guess what happens? It can pass through the external circuit. The electron combining with the hole, that will create a voltage difference, so it's going to drive a current. So current will be produced in that external circuit. I can simply just sit back and measure that current, and it is directly proportional to the number of photons striking the PN region, isn't it? I can build a light detector measuring the photodiode current. So sure enough, this is an easy thing to do. And the great thing about these silicon photodiodes, really inexpensive and really small. You can make them very, very, very small. Okay. People have gotten really, really good at building these tiny little semiconductor technologies. And what's the significance of making it really, really small? Well, I'm getting kind of moving into the next section I want to tell you about, okay? But there's a newer type of spectrophotometer that has been developed that it's pretty much taken over the field right now. And it's actually based upon photodiode arrays, as they're called. Now I mentioned one of the advantages of photodiodes, not only are they really cheap, but you can make them super small, like even like micrometer size, potentially. So why not, if that's the case, get really good at making these and make an array of photodiodes. Let's see what we mean by making it an array. Basically what I'm describing is that I can build one photodiode. I'm going to call it PD1 for photodiode 1, right there on a long strip. But if I'm really good at making these photodiodes, maybe I can put another photodiode right next to it. That's photodiode 2. And then why not make photodiode 3 right here? Photodiode 4. I could just make an array of these really close together, like sequentially, right? In a line, basically, on down. And maybe if I'm really good at this, I can make 1,064 of these along this axis, or maybe even double that. Maybe I make 512 if it's a little bit lower density. But you get the idea. I can make a huge number of these tiny little micrometer sized photodiodes side by side by side from one side of a device all the way over to the other. And this is called an array of photodiodes, or photodiode array, what I'm describing here. PDA, okay? Now, why in the world would this be interesting from a spectroscopic point of view? Well, because they can be used to make what's called a photodiode array spectrometer, which has several advantages, okay? Let's say that you have your light bulb, which is your continuum source of radiation, okay? And you take that light from that light bulb, you pass it into your monochromator. Well, wait, hold on, let's not do that. Let's say that you pass it through your cuvette first, okay? Pass the light through your cuvette. Out the other side. So this is your sample S, okay? Out the other side. And let's just say that you've got one of those gratings here. I'm going to draw it at an angle just to kind of show the reflection off of it, okay? But this is one of those diffraction gratings that we talked about. We build the monochromator out of, right? So what might happen? Might it be possible that red light diffracts off that way? And maybe yellow light diffracts off this way, and green light, well, it's going to maybe diffract off this way, and blue light diffracts off this way on our photodiode array. And then maybe down in here, I could even do UV wavelengths. I think you're getting the idea here. In this type of design, photodiode array, the wavelengths spread out along the axis of the photodiode array. And each photodiode senses or measures a particular specific wavelength. Each individual photodiode senses a specific wavelength. Maybe it's just 1 or 2 nanometers wide, but each photodiode can act as its own independent light detector. And each photodiode senses a very specific, very narrow wavelength range, independently from the others. Well, let's think about what might be an advantage to this. Does this device need moving parts to scan the wavelength? Remember before I said that what you do is you'd attach a rotating cam to this grating. To change the wavelength, you have to scan it. Does this need that? Nope. No moving parts at all. Usually means less things to break, right? But there's another key crucial advantage as well. What if you wanted to record an absorption spectrum on one of those devices where you had to tilt the grating angle? Would that take you some time? And think about it, you'd have to tilt it to one wavelength, make your measurement, then when you're done, tilt it to the next wavelength, make your measurement, third wavelength, make your measurement. It sounds like that might take a while, right? That's generally true, and even if you have a mechanized approach, it might take a minute or two to scan an entire wavelength range. But this photodiode array instrument is completely different because there's no moving parts. I can record a super fast spectrum. Even in the millisecond time range, way less than a second, I can get a complete spectrum because there's no parts that have to move. I just need to wait for a very short period of time, until each of my photodiodes gets sufficient light to accurately measure it and read out that signal to a computer. All that can occur very, very fast. So this photodiode array spectrometer has the advantage of taking millisecond type spectra, which is really unheard of before this photodiode array device was I should say discovered, but developed. Okay. So for these reasons, no moving parts, extremely fast spectra over wavelength ranges from the UV to the near IR. Because of these reasons, these photodiode array spectrophotometers have really taken over in the lab. And the other designs I'm going to tell you about in the next video are almost historical at this point. This PDA or photodiode array spectrometer, almost everybody uses them because they get very, very, very fast spectra. So this solid state technology really has led to pretty important advances. Okay, so I'm going to end the video here because it's a great place to stop. And then we're going to come back and talk about putting these parts together to build UV-Vis spectrophotometers.